Okay, now we'll go through some example problems related to Faraday's law and induced EMF and electric fields. So, in example 31.1, it says that a coil consists of 200 turns of wire. So, capital N is 200. Each turn is the square of a side 18 centimeters. So, area will be multiple of two sides, and a uniform magnetic field directed perpendicular to the plane of the coil is turned on. If the field changes linearly from 0 to 0 0.5 Tesla in 0.80 seconds, it means that the initial time will be 0. What is the magnitude of the induced EMF in the coil while the field is changing? The given data is number of turns, side, delta B, and time, and we have to find induced EMF, and area will be 18 multiplied by 18 centimeters square. The solution of the problem will be E, that is the induced EMF, is equal to N d phi by dt. Here d phi by dt is delta phi and over delta t, where we know that phi is equals to BA. So here A will be 0.18 square and B is changing with time. So we have zero point 0.5 minus 0 divided by 0.8 minus 0. By solving it, we will get 4 volts. In example 31.2, a loop of wire enclosing an area A is placed in a region where the magnetic field is perpendicular to the plane of the loop. The magnitude of B varies in time according to the expression. So here we have an expression for B, that is B maximum into E minus AT, where A is some constant. That is at t equals to 0, the field is maximum. So if you place t equals to 0 in this equation over here, e raised to power 0 will give us 1, and we have v equals to b maximum. And for t greater than 0, the field decreases exponentially. So if we have the value of t greater than 0, then it will decrease exponentially. Find the induced EMF in the loop as a function of time. Okay, let me erase this. All right. So the given data is area, and B, the expression for B is given. A is a constant, t equals to 0 when B is maximum, and t greater than 0, then B decreases exponentially, and we have to find induced EMF. Simply we will use this equation over here, and we know that 5 is BA. So we'll write the value of B over here, that is B maximum e raised to the minus 80. So what we'll do, we have D e raised to the power minus EA t minus AT over dt. So after taking the differential, I get a small a, capital A, B maximum e raised to the minus AT. So when I place t equals to 0 over here, I get E induced EMF maximum value, that is equals to small a, capital A, and B maximum. Okay, now this example problem is related to induced EMF and electric field. So if you have a long solenoid of radius r and n turns of wire per unit length, and carries a time varying current that varies sinusoidally as I equals to I max cos of omega t, where I max is the maximum current and omega is the angular frequency of the alternating current source, as shown in figure over here. So the direction of the current is given, and we have a solenoid. The radius is capital R. We have to determine the magnitude of the induced electric field E, capital E, outside the solenoid at a distance r greater than capital R from its long central axis, and for B, what is the magnitude of the induced electric field inside the solenoid a distance small r from its axis? So the given data is radius of the solenoid, turns, and turns, and small n is number of turns per unit length. This is turn per unit length. So, and I is given, we have to determine A. So the magnitude of E at R greater than capital R is, we have seen while doing the article that minus d phi b over dt is equals to minus d over dt ba, and here area is pi r square. So I have replaced the area, and this is equals to minus pi r square dv by dt. Also, we know that B is equals to mu naught n I, and the value of I is given in the problem, which is I maximum cos of omega t. So, putting the value of B over here, and we'll see that we will be differentiating cos of omega t with respect to t, and the value that we'll get is pi r square mu naught n I maximum omega sine of omega t. So what we are supposed to find is the magnitude of E, and we have seen in the article also that closed integral E dot ds is equals to open surface B dot dA, and we have this equals to closed integral E dot ds is equals to E into 2 pi r. This is the small length element, but after integration we get the circumference, that is 2 pi r. And now equating 1 and 2, equating this and this over here, so we have E into 2 pi r equals to the value of minus d phi b over dt. So putting in the values and solving it for E, and here is what we get for small r greater than capital R. Now, what is the magnitude of the induced electric field inside the solenoid a distance r from its axis? So again, we have minus d phi b over dt, which is equals to minus d by dt b into area, and writing this equation again, solving it the way we have done in part A, and we get this. But now we have radius equals to small r over here. For closed integral E dot ds, we have this on the left side, equating these two, and now we get the value of E equals to small r mu naught n I max omega sine of omega t divided by 2 when we have small r less than capital R, that is lying within the solenoid. So these